Good afternoon to everybody. I'm Alfredo Battistelli, and I've been invited by the International Geothermal Workshop Committee to give this speech about current and future challenges in reservoir modeling. Actually, I would like to talk more about the capabilities we already have rather than challenges, but let's go to the outline. We will talk about reservoir modeling workflow, the conceptual and reservoir models, the reservoir simulator, inverse simulation capabilities, thermodynamics of geothermal mixtures, the use of tracers in numerical simulation, supercritical condition, modeling of non-condensable gas injection, coupled Wellbore reservoir flow, and geochemistry and rock mechanics. So this is the typical reservoir modeling workflow for a new field without production history. So we start from field data to build a conceptual model, and we would like to use a 3D geological modeling software. From the conceptual model, we build the natural state model, in which we can already consider the planned production and injection wells for the field development. Then we use the static pressure and temperature logs and the data collected with production, interference, and tracer tests to calibrate the natural state model. And we need inverse simulation capabilities for that. Once the model is calibrated, we build the exploitation model considering the requirements for the fluid collection and injection system and the plant requirements. How much steam can we produce? Then, once the exploitation model is ready, then we can simulate forecast scenarios. So we need a reservoir simulator, inverse simulation capabilities, which can be integrated into the reservoir simulator, and Wellbore simulator and simulation capabilities for the exploitation model. They can also be integrated into the reservoir simulator. When we go to the modeling of an exploited field, what we have is the field production history, so that we can build a production model and perform the calibration in order to match the past production history. Once this calibration is achieved, and it may need also to recalibrate the natural state model for that, then we can build the exploitation model and again simulate the forecast scenario. What is the conceptual model? I mean, what we have to use for the conceptual model? We want to use a 3D geological modeling framework. And this modeling framework should also be integrated with the reservoir simulator, because we want to build the discretization grid and the input files for the reservoir numerical model within the same modeling framework. And the conceptual model code shall also be able to visualize the simulation results. Examples of this, which are not exhaustive, of course, are Leapfrog Geothermal, which is a 3D geological modeling integrated with TUF2, which is actually given all of this stuff. And there is Petrel EMP software platform, which is integrated with Eclipse Geothermal, which is also able to do that. Other pre- and post-processor with less developed geological modeling capabilities are Petersim, and this is an example of a model developed within Petersim at the conceptual level, and then the model, the grid built for TUF2. Another pre- and post-processor is TUF2 Viewer. What we have to model? We do not have to model just the reservoir, but the reservoir with a well field, the production wells producing at separation stations, and the injection wells in which the separated brine is reinjected. And the steam is sent to a turbine with a turbine inlet pressure, and then the steam is condensed, and a fraction of steam, usually between 25 and 30%, is recovered and is reinjected back into the reservoir. So what we would actually like to do is to simulate everything. So the numerical simulator required capabilities. Of course, it has to solve the non-isothermal mass and then heat transport of multi-component, multi-phase fluid mixtures in porous and fractured media. We would like to have discretization grid able to follow geological features and allowing grid refinement around the wells. We would like to have stable convergence and fast solution of balance equations. Integrated wellbore flow simulation with wellhead pressure control, and a basic integration with a fluid collection and reinjection system and the plants, and the activation of makeup wells for global steam rate support. So, which are the new geothermal reservoir simulator? They are built with updated programming languages in Fortran 90, 95, 2003, and C++, with object-oriented programming. They allow parallel simulation in multi-core machine, cluster, and supercomputers. They have faster linear and parallel solvers and improved phase transition and steady-state convergence behavior. Examples are TAF3, developed by LBNL, ITAF2, and then the new version of the code, also developed at Lawrence Berkeley National Lab, Wildera, which is developed at the University of Auckland, and Eclipse Geothermal, developed by Schlumberger. Now the inverse simulation. This is the basic workflow by ITAF2. So you see that we first set initial model parameters. With the model calculate the system response, then we compare calculated results with measured system response at the field in an object function, and then through a minimization algorithm, we update the parameters in order to improve the reproduction of the measured data. So that we go through a trial and error procedure. We go to the calibration of the input parameters of the model. Now, thermodynamics of geothermal mixtures. I mean, geothermal mixtures are mainly composed by water, of course. So that water, the thermodynamics of water and water properties shall be computed in an accurate way. Usually now we are using the International Association Properties for Water and Steam, the 97 correlation updated in 2007. This is a pressure and temperature diagram in which the only physical boundary is the saturation curve of water here, while the regions labeled as 1, 2, 3, and 4, 5 are regions for different correlations, different equations. Once we add, and you see that in the subcritical simulation, usually we go up to 350 degrees C, which is the boundary of the liquid region with a supercritical one. There are already other codes able to simulate supercritical conditions. If we add CO2 here, or sodium chloride, we have strong changes of the phase behavior of the mixtures. So usually in the more general case, when we model subcritical mixtures, we would need a mixture of water, sodium chloride, and CO2. But we chart the most used equation of state module for TAF2 and TAF3. US1 for pure water, US2 for water and CO2, and EWAS-G, which is a three-component model for water, sodium chloride, and one non-condensable gas, usually CO2. Other codes with capabilities for three-component mixtures are TETRAD, STAR, and TAF plus RGB. TAF plus RGB is for real gas brine developed at the Lawrence Berkeley National Lab. Improvements. We would like to have the thermodynamic equilibria suitable for high partial pressure of CO2 with improved mutual solubility models and calculation of CO2-rich phase properties. There are already codes doing that, or at least partially doing that, as CCO2N, developed at Lawrence Berkeley, It was G, the version included into top 3. There is TM gas, which has been developed for modeling of gas mixtures into geological structure. Again, TOF plus RGB. And we would like also to be able to model mixtures of gases. And codes already able to do that are Eclipse Geothermal, TMVOC, which has been developed not for geothermal application, but can be used also for that. And again, TM gas and TOF plus RGB. Tracers. The main purpose of tracer is to study the connection between injection and production boreholes in order to predict the possible cooling of production boreholes due to long-term reinjection of spent brines. There are tracers for suitable for the liquid phase, for the steam phase, and for the two-phase conditions we can find in the reservoir. And the consolidated interpretation with analytical and semi-analytical approaches as described by Axelson. But we can move to numerical modeling. The rigorous thermodynamic approach for partitioning of gas and liquid tracers between the liquid and the steam phases has been developed for TAF2 by True et al. In 2001. Now there's a new equation of state module, US1 NT, available for ITAF, which allows the partitioning of the tracer using a Neris law for multiple tracer with absorption and decay. And also TM gas can simulate multiple gases and dissolved solids with generalized absorption isotherms and decay of all components. And these can be used as tracers. Let's go to supercritical conditions. Well, we can find supercritical condition when drill deep wells in already exploited high-temperature hydrothermal systems. But when we simulate this kind of reservoir with approaches, with subcritical approaches, we can get something like that. This is a model for a field in Kenya, in which wells at 2,000 meters and over the upflow were already measuring more than 400 degrees C. So we were obliged to cut the model in the basement in order to avoid supercritical temperature. Actually, supercritical condition can be modeled already by ITAF2 US1 SC, which provides modeling capabilities for pure water covering the entire PT space of the IF97 correlations. Another possible code is TAF2 US2H, which is for mixtures of water and CO2 that can be used at subcritical condition and steam-like supercritical condition. Steam-like means that we cannot model the region 3 of the PT space because those correlations are not used. Now about the non-condensable gas injection. Usually, non-condensable gas are discharged to the atmosphere, but this practice is becoming an issue, even though the life cycle greenhouse gas emissions of geothermal plants are among the lowest. Why? Because non-condensable gas emissions is becoming a concern for the public acceptance of old and new power plants in some country, and I would mention Italy. Moreover, greenhouse gas emissions of geothermal power production might hinder future funding of geothermal projects by international finance institutions. So there are pilot projects and research projects in several countries in order to study the feasibility of non-condensable gas injection, reinjection in the geothermal reservoir. But in order to do that, we need modeling capabilities for that. So considering a non-condensable gas injection schemes are the reinjection of a pure CO2 or non-condensable gas mixtures the injection of NCG dissolved in condensate or in the brine, or the co-injection of two streams of non-condensable gas and brine in the same well. So from the simulation point of view, reservoir simulators are needed with equation of state module able to simulate high-pressure CO2-rich mixtures in equilibrium with sodium chloride brine, and coupled Wellbore reservoir flow capabilities, which include CO2 liquid gas phase transition in injection wells. An example is T2 well ECO2M. T2 well includes Wellbore flow modeling capabilities into TAF2, while ECO2M is an equation of state module for ternary mixtures with a good thermodynamic approach up to 300 degrees C and 600 bar. It can model three-phase flow, phases of CO2-rich gas, or liquid CO2 and brine, both in the wellbore and the reservoir, and transient wellbore flow in cylindrical and annular conduits using the drift-flux model. This is just an example of pressure flowing pressure profiles in the injection well and flowing temperature profile and the injection well. So now about the coupled wellbore reservoir flow. Modeling of wellbore flow is actually needed for a variety of purposes in both reservoir engineering and modeling studies. Customarily, steady-state wellbore simulators are used for basic applications that fall for when we need transient solution of coupled wellbore reservoir flow, then we need additional capabilities. And these additional capabilities can be very useful for the interpretation of well tests, both completion and production tests, and for the production forecast simulation with wellhead pressure control. And again, T2 well can provide full transient coupled wellbore reservoir flow capabilities for the TAF2 family of reservoir code. An example is EWAS-G coupled to T2 well, which has been used to model at the same time the well output curve, the flowing pressure and temperature profile, and the pressure transients downhole during a short production test performed at WW01 Watton Waven field in Dominica. But coupled reservoir flow is very useful if we need to simulate production forecast scenarios with a wellhead pressure control of well discharge. So instead of controlling the well production using a well deliverability model with fixed bottom of pressure, we use a fixed wellhead pressure to control the well discharge. And Flowwell is a wellbore simulator which has been integrated into ITOF2, and it provides such capability for vertical or directional wells producing from multiple feed zones with a limitation of pure water reservoir application. Similar capabilities have been also implemented in TAF2 US2 for H2O CO2 mixtures with wellhead pressure control, evaluation of steam rate at the separation station, and the activation of makeup wells. This has been done by Saipan and Marcolini and Battistelli in 2012. And also, these capabilities are available in a TAF2 version in which the well flow wellbore simulator has been coupled by WestJet. Now, just to complete, something about geochemistry and geomechanics. Actually, there are geochemical capabilities, modeling capabilities developed in TAF-REACT, a well-known code, and geomechanical capabilities in TAF-FLAC. This is the old version. The new version is TAF-3-FLAC 3D. And then there are also new codes in which both geochemistry and geomechanics are can be solved together. Geochemistry is usually, geochemical capabilities is usually used for mineral alteration and silica scaling in a hydrothermal system under natural and production injection conditions, while geomechanics capabilities are almost used for fluid and heat flow and stress-induced phenomena such as formation compaction and ground subsidence, stress-induced changes in the reservoir properties, and borehole failures. This probably will be application that will find quite a lot of interest in the upcoming times. So thank you a lot for your attention, and thanks to the International Geothermal Workshop Committee for its kind invitation. Bye.
Hello everyone, my name is Aviat. I'm a student from Geothermal Engineering Master Program, Institut Teknologi Bandung, Indonesia. On this occasion, I will present our research on reservoir simulation with the title Non-Condensable Geothermal Field Conceptual Model based on natural state modeling. This research was conducted by researchers from Institut Teknologi Bandung and the PLN or National Electricity Company in Indonesia. Broadly speaking, this research was conducted with a study related to the background of geothermal exploitation in this region. Geoscience studies are carried out to determine the features and characteristics of the geothermal field. As an initial exploration step, geoscience studies produce temporary conceptual models that will be updated in this study. Adjustments are made to form an appropriate simulation model in order to obtain results that are close to the actual natural state. Updated conceptual models are generated from natural state modeling results. The Dana-Ronald Geothermal Working Area was established through a decree of the Minister of Energy and Mineral Resources in 2011. The geothermal field is located in the Lampung and South Sumatra province, with an area of around 127 square kilometers. The Dana-Ronald Geothermal Field is a virgin geothermal field assigned to Indonesian National Electricity Company to be developed. Until now, the exploration stage that has been carried out by the National Geological Agency only has limited data, which depends only on geoscience studies like geology, geochemistry, and geophysics. The results of the integrated geoscience studies are used to estimate the conceptual model of the Dana-Ronald geothermal field. At this field, there are no exploration wells or gradient temperature wells that have been drilled in this area. However, we assume that the results from geoscience are enough to support the physical parameters needed by the numerical model to be developed, including reservoir geometry, reservoir temperature based on geothermometers, and estimation of subsurface rock physics. Numerical model simulation is expected to be able to overcome the shortcomings of geological conceptual models and provide more precise and accurate estimation of subsurface features. The Ronald geothermal field is a Pleistocene caldera from Mount Ronald formed on the Sumatra fault system, which formed a basin due to the formation of a pull-apart fault system. The southeastern part of the Ronald formed Mount Seminung, which is a stratovolcanoes-type post-caldera mountain. The products of Mount Seminung are lava and pyroclastic that show explosive eruption with high energy. According to the appearance position of the manifestation, it is estimated that the remaining magma erupts as a heat source of the emerging manifestation that originate from Mount Seminung. Permeable zones in the Dana-Ronald geothermal field are controlled by Sumatran fault system, which is a strike-slip fault with a dextral-moving direction that is relatively directed to the northwest-southeast. The separation of the fault section by step-over with an echelon pattern results in the formation of extension movement that forms volcanic tectonic depression at Dana-Ronald. And then the neuronal geothermal field is indicated by the presence of surface manifestations in the form of hot springs and warm springs, without any streams of gas manifestation indication in the surface. A detailed study of this report was carried out through 10 data of surface manifestation of thermal spring consisting of 4 hot springs about 55 to 63 degrees Celsius and 6 warm springs less than 50 degrees Celsius that spread on the slopes of Mount Minung following northwest-southeast fault direction, which is Cotabato Fault, and northeast-southwest fault, which is Lombok Fault. The geothermal hot springs and warm spring distribution is limited to only those two areas, whereas in the southeast section there are traces of the hydrothermal process in the form of argillic alteration on the surface, which is also associated with the northwest-southeast faults. Travertine deposits are also found to be associated with the presence of several thermal springs, followed by high bicarbonate value. The quality of manifestation data based on the ion balance analysis is excellent, with an ion balance value of less than 5%, based on Nicholson geochemistry standard published at 1993. The Longbiak and Cotabato fault act as a permeability structure based from gravity and magnetic method, and the low resistivity value found at depth of 200 to 500 meters below, with thickness about 500 to 1000 meters. Based on the geoscience study, the conceptual model of geoscience that can be produced is what is seen on this slide. This geothermal field is high-terrain geothermal system that created by post-caldera eruption. The reservoir temperature is between 200 to 210 degrees Celsius, which Mount Minung acts as geothermal heat source. The outflow are located at northeast region. It is Cukuh, Waiwangi, Kota Batu, and Kerincing manifestations, which the richest area spread over area of 54.25 square kilometers, mainly in steppe hills around Mount Minung. This research methodology is in developing the natural state reservoir model consists of several steps. It starts with collecting geoscience data and conceptual models from the latest study. A computer numerical model based on the conceptual model is made using a TAF2 simulator to simulate fluid and heat flow process of the geothermal system. This numerical model consists of grid blocks in which each block is assigned with the material properties. Top, bottom, and boundary conditions of the model are set based on the conceptual model. The model is run to get the result of the model. The material properties, top, bottom, and boundary conditions are calibrated iteratively to obtain the best match between the model and the conceptual model, which indicates that the model successfully represents the natural state condition of the reservoir. This model uses EOS-1 for water non-isothermal because of the data limitation and to simplify the modeling process. The grid of the model is rotated at 30 degrees to the north to accommodate the material assignment to be necessary in arrangement with the alignment of the conceptual model. Simulation model covered based from surface manifestation and permeable faults distributions in these geothermal fields. The adjustment of grid size depends on the reservoir and permeable structure predicted position from geoscience maps. It covers a total area of 10 kilometers times 4.6 kilometers, or equal to 46 square kilometers, and a total thickness of 2.50 to 3.37 kilometers. The horizontal dimension of grid blocks varies from the smallest 200 meters times 200 meters to the biggest 474 meters times 474 meters. The smallest grid size is set to accommodate more detailed calculation on the reservoir part. The model is divided into 8 layers and 11 sublayers, with some of the top layers following the real topographical condition. The total number of grid blocks is about 11.5 thousand pieces by using rectangular grid type. Some pieces parameters are determined to form a model that approach the real situation in this geothermal system, which is hydrostatic pressure and normal temperature gradient were used at initial condition. The top boundary was set to be in atmospheric condition. Material in line with fault defined to be more permeable. The side boundary was assumed to be no flow boundary and treated to be impermeable materials. Bottom boundaries are heat source and impermeable rock or bedrock. The model consists of 8 layers that define based from general, medium enthalpy, high terrain geothermal system. Rock density, porosity, permeability, thermal conductivity, and specific heat capacity was defined. The initial condition is needed to input the initial temperature and pressure for each grid block on the model to fasten the process in running the model. At the initial condition, the normal gradient is used for both temperature and pressure. Atmosphere is applied to the top boundary condition by assigning pressure and temperature in the atmosphere or surface are homogeneously at 1 bar and 25 degrees Celsius respectively. Lake water in the runoff area is modeled as a material composed of water, so it is defined as a separate material layer. It is done to accommodate the calculation of the existence of lake water intrusion in the geothermal system. Inside the boundary, it is assumed that there is no flows of fluids. All the side boundaries are in impermeable conditions, which is there are no flows of both heat and mass coming into or going out the system during natural state conditions. To get optimal and reliable results, some adjustments are made to get results that are in accordance with their natural state. Some of them are by adjusting the temperature and pressure of the heat source, adjusting location of heat source in bottom boundary, adjusting permeability structure in X, Y, and Z directions, adjusting material properties such as porosity, rock density, thermal conductivity, and specific heat. Adjusting the size grid blocks of caprock, reservoir, and heat source. Based on the simultaneous process, the distribution of permeability gives impact to ability of rock to flow, the fluid and flow distribution of temperature, conductive and convective heat transfer. Convective heat transfer may occur in permeable zone or reservoir, and conductive heat transfer may occur both in the permeable and impermeable, like reservoir and caprock or the boundary. So based on the result of numerical modeling of natural state, the model determined reservoir characterization. 2 dummy wells were made to represent the hot spring manifestation at the Narano geothermal field. Dummy wells are simulated by setting the well deliverability value at atmospheric pressure and certain productivity index to fit mass flow based on the field condition. In the process of emulating the model, subsurface temperature validation was carried out based on the 3D isothermal estimation method based on the idea of calculating subsurface temperature gradients. The calculation is done by determining the reservoir temperature based on the geothermal and reservoir and temperature of the surface manifestation. Then the subsurface temperature for each depth can be obtained. Boiling point versus depth, or BPD curve, are plotted to determine the characteristics of the reservoir. Based on the BPD curve, the interpretation shows that the reservoir is in compressed liquid state. This can also be confirmed from the SG or synthetic gas value in the simultaneous results. This figure shows the temperature of and pressure profile of dummy well 1, dummy well number 2, and dummy well number 3. They are located on the outflow zone, and then on the dummy well 3 that is located at the upflow zone, or that we create for this model. So we get the updated conceptual model shown in the figure, was designed based on a preliminary geoscience study without any well data and submitted to create a numerical model approach. It appears that hot geothermal fluid flows upwelling from the deep part of monsoonic magma intrusions to the surface by rock permeability and porosity. The deep leakage of fracture permeability from Talang Biak Fault and Kota Batu Fault control the flows of hot fluid that ascend through the vertical permeability with some fluid flow in the lateral direction. In contrast to the initial model, there is a change in determining the depth of the top reservoir as the updated model has followed the interpretation of magnetotelluric. It is stated that the top reservoir of Lombok geothermal area is situated around the depth of -500 mean above sea level. The only exception applied for the Kota Batu area in which the reservoir reached the depth of -700. The geothermal line is determined based on the contours of subsurface temperature variation resulting from natural state modeling. The shape of the contour and the distribution of temperature factors are then adjusted to the available geoscience information. Contours and mass flow pressure factors show undulation patterns according to the geothermal field condition of the high-terrain volcanic system. To summarize, reservoir numerical modeling can be done by preliminary study data. The first natural state modeling of Danau Ranau geothermal field has established successfully by only the geoscience and Indonesian volcanic hydrothermal system approach. The mass and heat flow profiles predicted for new conceptual model. Range of productive zone or reservoir are between 13.65 square kilometers and 16.68 square kilometers, which reservoir shape is like a dome. Maximum reservoir temperature is 269 degrees Celsius, and geothermal system is liquid dominated. This natural state model can be used to predict the condition at the unexplored part of the reservoir. The conceptual model will continue to update it based on the additional exploration information to be carried out. Natural state modeling can be improved by adding subsurface information with exploration well, but both thermal gradient wells and slim hole wells. As an initial step of feasibility study, this model can be used to determine resource assessment using the Monte Carlo simulation method. This is the end of my presentation. Thank you for your attention.
Geothermal energy is a relatively environmentally friendly source of energy. It is derived from the heat of the earth. In recent years, the market for geothermal power has increased sharply, especially in emerging markets due to the economic growth due to the growing number of communities in low-income rural areas that have access to the power grid. Any governments are also increasing focus to reduce the dependency on expensive fossil fuels and not environmentally friendly. Systraco Group is a company engaged in the energy sector. Established in 1995, Systraco Group is currently very focused to be able to develop and serve you in various needs related to the geothermal sector, which among of them are hole cleaning services. Systraco Group provides comprehensive conventional fishing tools and systems include packer milling and retrieving, internal and external cutting, internal and external engagement, washover, basically every fishing application. Regardless of what's in your well, hence we've removed it successfully. We also provide a radial cutting torch that is safe and without any explosives or harmful chemical elements that can cut the tubular drilling equipment left in the well. As well, biochemical that can scale control, corrosion control, cooling water treatment and also as a rig washer. Downhole camera. Leveraging the advancement of technology today, Systraco Group also provides high-resolution downhole camera equipment and clear image quality and capable of operating up to a depth of 2,000 meters, adding to our line of services to focus on the development of the geothermal sector. Geothermal well testing. Energy Megaperseta, as the sister company of Systrico Group, also provides the services of geothermal well testing, real-time well monitoring, geoscience. Digital remote sensing use Sniffer 4D drone. Digital remote sensing system has an advanced capability to detect and map for the following energy sector applications: steam surface breakout monitoring, well reliability and integrity monitoring, air quality mapping, well surveillance and inactive well management, geothermal associated gases detector and mapping. All of which are focused to support activities in the geothermal sector. Please, do not hesitate to contact us when you need our support, because we are there for our common progress. Thank you very much.
Okay, good morning. Selamat pagi. I am Jonet Hendra Sakti. I'm going to present my work with Maulida Rahma with the title Numerical Study of Temperature Profiles of Present Flow in Geothermal Oil Field. The background of our works that first there are so many obsolete oil or gas wells that have potential moderate temperature of 50 about 100 degrees centigrade to be used for geothermal applications. So we want to know if this oil or gas wells is feasible for direct use geothermal utilization, because it is not common yet in Indonesia right now. So we want to analyze using numerical methods, since it is hard to measure or to calculate possible temperature as accurate as possible analytically. So the objectives of our study are: first, we want to generate the transient computational program of oil field geothermal gradient temperature using MATLAB. Second, we want then compare the result of our program. We want to compare the temperature profiles in the drill pipe and annulus as function of circulating time using current program compared to the literature simulator. We want to analyze then, after we compare, we analyze the feasibility of geothermal utilization in Arun field and BN field or in the BK area. In the building our program, we use double pipe heat exchanger, and this is coaxial double pipe heat exchanger. We divide it into 5 regions, and the first regions is right here. This is the drill pipe region. The second region is drill pipe wall. This is between the region 1 and region 3, which the region 3 is the annulus region. And the fourth region is the interface between annulus and the outer pipe wall. And the fifth region is rock formations. The water is injected from at the region wall, region 1, or at the drill pipe, and then until the bottom of the well, and goes up and extracted into annulus. And this is the numerical simulation scheme that we use. The first and the second, of course, is the continuity and the energy balance equations. These are that you can see here from the equation right here. This is only in the R and the Z direction. And also in the energy balance, also only in the R and Z direction. We didn't calculate for the theta directions. And also there are lowercase t here indicate this is the program for the transient flow. These two differential equations are then converted into arithmetic equation, the one right and the left. This is the the simplification. And then after that, we can generate a big matrix to calculate the T1, T2, T4, and so on at a specific time. So if you can see this equation here, we have the subscribe, for example, M here indicate the location or the spatial, and then the superscribe indicate the time index. So the other parameter in our computational program are, for example, we need to know the water properties, rock formation properties, oil field data, fiber of design, and so on. We calculate the loss coefficient, and we have to know the boundary condition, for example, water injection temperature, water injection mass flow, and surface ground temperature. And we also need to know the initial condition, for example, water extraction temperature, surface temperature for region 2 and 4, and bottom hole temperature for region 1, 2, 3, and 4. The program that we build, they has the main program and 18 subroutines. The 18 subroutine, for example, there are initial gradient subroutine, velocity calculations, and so on, including at the end, for example, here is saturated water enthalpy or the properties of the water. So the validation of the Kawan program, we compared with the Wellbore model from Santoyo, Gutierrez, 1997 as reference. In comparison, the pipe diameter is about 0.2191 meter, the depth is 6100 meter, with the drill pipe diameter of 0.1143 meter. With operating condition are fluid flow rate of 15.14 kilogram per second, geothermal gradient temperature of 0.0292 centigrade per meter, and inlet fluid temperature of 57.2 degrees centigrade. And the result here that we can see here on the left for the drill pipe fluid temperature. On the right is for the annulus fluid temperature. So this is on the coordinate is the depth. We have until about 6,000 meters, 6,100 meters. So the result on the drill pipe here, first we can see our results indicate with the straight line here, the red and the green color, while the Santoyo and Gutierrez results are indicated with the line right here. Little bit has a arc line here. So, and then the other straight line here, you can see this is the formation gradient temperature. So you can see here the result little bit different. Our program with the Santoyo Gutierrez program are different. Not exactly the same, but the temperature result is about the same. Yeah. So the difference itself is due to the lack of informations, such as like start in time, temperature, and so on, that we cannot find in the original work of Santoyo and Gutierrez. And although the result will be different, the temperature range remain about similar. So we are confident that we can use our program to do some feasible study. And almost forget here, this is the one on the right. This is the picture of the wellbore depth with the annulus fluid temperature. Similar to the drill pipe fluid temperature, we have the straight line results. Yeah, with almost about the same. So you can see here this the time, circulating time, about 2, 5, 10 until 24 hours. Again, the temperature, although is not exactly the same, but the range is about similar. So we are very confident we can use the program to apply to other locations. So these are the data we apply to other locations. The location that we use is the Arun field and then BK area or BN in the BN field. The depth is about 3,000 meter and about 700 meter with the temperature of the bottom is 178 for the Arun field and the BK area is about 99.17. Yeah. So with the diameter of inner pipe is given here. This is the first column here for the Arun, the second for the BK area. Also the water injection temperature, water mass flow rate also are obtained here. And then the BK field here, we have the other information like the temperature at the deepest point at region 1, 2, 3, and 4. Yeah. So these are the results when we apply our program into each field. On the left is the Arun, this is the depth. So this is, and then we have the temperature. So the depth is about 3,000. Yeah, the result also indicate that it has about 130, 140 degrees centigrade after 24 hours when we circulating the water. On the BN field, when we circulating until 24 hours, the temperature remain lower than 70 degrees centigrade. So we can conclude that in the Arun field, it has about the maximum 130 degree. We classify it as geothermal source as moderate temperature source. For the BK field, this temperature about 80 degree. We don't think that's going to be higher than that. We classify into low temperature source. So in conclusion, that we have developed the transient computational program of oil field geothermal gradient temperature using MATLAB. And the results is, although it's little bit different from the result by Santoyo and Gutierrez, the results are similar. So we are very confident. So when we apply into the oil field, the obsolete oil field, for example, Arun is feasible as the moderate temperature, while the BN field is feasible to be converted into the low temperature geothermal source. Thank you very much, and I hope you enjoy our presentation. Thank you.
Indonesia merupakan salah satu negara yang memiliki potensi energi panas bumi terbesar di dunia. Saat ini, Indonesia menduduki peringkat 2 dunia sebagai negara penghasil listrik dari energi panas bumi. Selain sebagai energi yang bersih dan berkelanjutan, peran energi panas bumi sebagai baseload penyediaan listrik menjadi pertimbangan utama agar pengembangannya diprioritaskan. Oleh karena itu, dalam menjaga ketahanan energi suatu negara, energi panas bumi dapat menjadi andalan untuk memasok listrik guna memenuhi target bauran energi 23% EBT di tahun 2025, sesuai dengan amanat dari Kebijakan Energi Nasional. Untuk memenuhi pencapaian target EBT, dalam bauran energi tersebut, Indonesia layak melakukan percepatan pembangunan proyek PLTP di Indonesia. PT Geodipa Energi Persero adalah perusahaan yang bergerak di bidang energi panas bumi mulai dari eksplorasi hingga eksploitasi. Perusahaan didirikan pada tanggal 5 Juli tahun 2002. Kemudian pada tahun 2011, melalui Peraturan Pemerintah Nomor 62 Tahun 2011, Geodipa ditetapkan sebagai Persero yang pengawasan dan pembinaannya berada di bawah Kementerian Keuangan dan PT PLN Persero. Yang yang juga merupakan salah satu Special Mission Vehicle atau SMV di bawah Kementerian Keuangan dengan misi mendukung program pemerintah dalam penyediaan listrik tenaga panas bumi yang aman dan ramah lingkungan, serta memberikan manfaat besar kepada Indonesia. Geodipa siap untuk melanjutkan pengembangan proyek PLTP Dieng Patuha yang masuk dalam Fast Track Program atau FTP, tahap 2 10.000 MW. Bagian dari program 35.000 MW yang merupakan program pemerintah di bidang pembangunan infrastruktur ketenaga listrikan.
Hello everyone. First of all, I would like to say thank you for the opportunity. My name is Zagia Kanaberian as the first author and Mr. Hendy Rianto as the co-author. In this occasion, I would like to present our work with a title, A System Design of a Solar and Geothermal Hybrid Power Plant for the Flores Island. This is the outline. The first is introduction, the second is the literature review, the third is methodology, the fourth is the result and discussion, and the last is conclusion and recommendation. Indonesia has abundance of solar energy and geothermal energy, but Indonesia has the lowest electrification ratio and it has the problem because the challenging geographical characteristic in East Nusa Tenggara. One of the island, Flores, has abundance of geothermal and solar energy potential. So why don't we utilize more from the geothermal and the solar energy? And there will be a project development, Ulumbu 3 and 4. And in terms of generation cost, Flores has a high generation cost with a number of 0.175 USD per kilowatt hour. And this work will elaborate solar energy, storage energy, and geothermal energy to substitute diesel power plant in the evening. This is the local characteristic of the location target. This figure, electricity profile, show the lowest load is around 0 to 6, and the highest load is around 20 to 24. In terms of duration of sunshine, the probabilistic in Ulumbu around 4 to 8 hours. And this is the hybrid system literature review. There are 4 types of solar collector, but the most mature technology is the parabolic through concentrator. And this is the 2 alignment in solar tracker. The first one is north-south alignment, and the second is east-west alignment. For the north-south alignment, it means the solar tracker will track the sun from the east to the west. And for the east-west alignment, it means the solar trackers will track the sun from the north to the south. And it will be going to the thermal energy storage. There are 3 medias. The first one is sensible, second is the latent, and the third is the chemical. But the most technology and the most mature is the sensible. And this is the alternative configuration. The solar collector, it can be located in A1, A2, and A3. And this is the formula that this system use. The first one is the beam irradiance based on the specific location, and it can generate beam irradiance and diffuse irradiance, and it will convert to solar irradiation. The solar radiation can be found by calculate the area under the curve, and this is the heat exchangers and solar collector, geothermal, thermal energy storage, and carbon dioxide emission. This is the thinking framework. This system will operate with 2 conditions. The first one is the geothermal standalone. The second one is the hybrid. This is ways that the system will work. The solar radiation will collect by the parabolic through concentrator using the heat transfer fluid. And the energy will be stored in thermal energy storage. And the thermal energy storage will supply the energy to the heat exchanger while the peak load condition, the production well will go into the heat exchangers and then going to the steam power plant. But in this base load condition, the production well, it will be going directly to the steam power plant. And this table shown the day selected. It will be the same for the 3 last years from the 2017 to 2019. And this is the Ulumbu coordinate. to generate irradiance and irradiation more specific. The first one, obtain the irradiance data. Second is find the average irradiance data in each month. And the third is select the lower quartile to represent in its time. And this is the irradiation. The first one, generate function of irradiation using Excel regression. The second is input the LPM as an interval. And the third is find the average value between 2017 to 2019. The fourth is delete the outlier data. And the last is find the average value from the existing data. And this is the mass and energy balance. This work using the Aspen HYSYS to model the system. The first one is just the equipment for the power plant. For example, turbine, separator, valve, and the condenser. In this model, the difference between single phase and hybrid. There is a heat exchangers in a hybrid system, and then run the system between steam quality from the 0.56 to 0.71. And for the thermal system, this work will use the heat exchangers to exchange the energy, and will use the thermal energy storage. And the output will be the required energy for the parabolic through concentrator. And for the solar collector system, this work will evaluate for the two alignment, the north-south and east-west, and the output is the area solar collector. And the last is the storage system. It will be evaluated from the two alignment, and the output is the mass and volume of the thermal system. This is the carbon dioxide factor using life cycle assessment, and this is the model of hybrid system result. The system will operate standalone between 0 until 18, and it will be hybrid system between 18 to 24. This is the idea. While the sun is shining, the energy will stored to the thermal energy storage. When the evening, the thermal energy storage will release the energy, and it will be going to the heat exchangers. So the geothermal working fluid will going to the heat exchangers, and the steam quality will increase. When the steam quality is increasing, the mass of steam production after the separator will increase, and it will give the more energy produced for the turbine. And this is the TS diagram. From the state number 1, it will be going to the state number 2 in standalone condition, and from the state number 1, it will be going to the state number 2H while the hybrid condition. And this is the result of solar thermal energy potential. In this figure, we can see the more irradiance data in Ulumbu, it can be generated using the north-south alignment. And when we input the LPM data, the irradiation will gain the higher energy for the north-south alignment. So the system will choose the north-south alignment. And this is the local characteristic of the solar energy for the two alignment, east-west and the north-south. The system will use the north-south alignment and choose the probabilistic of 6 hours in the Ulumbu. And it will generate around 4 kilowatt hour per meter square. And this is the power plant. The power plant will operate in the two conditions. NCR means the normal condition rating, and MCR is the maximum continuous rating. The capacity will be 22 megawatt in NCR, and it will be 26 megawatt in the MCR. The geothermal mass flow rate, it will be the same for the NCR and the MCR with a number of 243 tons per hour. And for the turbine efficiency, it will be 78% for the NCR, and it will be 80% for the MCR. For the conversion efficiency, it will be 14% for the NCR and 15% for the MCR. For the steam quality, it will be 0.56 for the NCR, and it will be 0.66 for the MCR. And for the duration, 18 hours for the NCR, and 6 hours for the MCR. The thermal energy from the test, 0 for the NCR, and 80 megawatt hour for the MCR. The thermal energy from the PTC, it will be 0 for the NCR and 84 megawatt hour for the MCR. NCR is the geothermal standalone condition, and MCR is a hybrid system operation. And this graphic shows the power increases while the steam quality is increases too. For the thermal system result, in this system, we use the north-south alignment and choose the 6 hours of probabilistic of the duration of sanction, or the LPM. It will be needs aperture area around 3 hectares, and for the mass and the volume of thermal system, it will needs 5,000 HTF in the parabolic through concentrator, and it needs 4,000 HTF in thermal energy storage, and it needs the 3,000 meter cubic of the volume of test. And for the carbon dioxide emission, the system calculate the same amount of annual production with a number of 5,450 megawatt per year. And in these figures, we can see that the solar geothermal will reduce the carbon dioxide significantly. And for the geothermal standalone, it will reduce 18% of the carbon dioxide. And for the hybrid system, it will be reduced 93% of the carbon dioxide emission. For the conclusion, the system will be operate between 18 to 24, and it will be select the north-south alignment and required power from the parabolic through concentrator in amount of 14 megawatt, and it will be increasing electricity around 4 megawatt electric, and it needs the collector area around 3 hectares. For the thermal energy storage, the volume of the test is 2 times of 3,000 of meter cubic, and the annual carbon dioxide from the diesel power plant, geothermal standalone, and hybrid around 2,200 and 125 carbon dioxide equivalent per year. For the further recommendation, we suggest more details in design of tests, solar data conduct by the experiments, and conduct the economical aspects. And thank you.
Good afternoon, ladies and gentlemen. Before I start this presentation, I want to give thanks to ITB International Geothermal Workshop 2020 Committee that have conducted this event. First, I want to introduce myself. My name is Andrian Mutawadana. I am from Geothermal Engineering Master Program, Bandung Institute of Technology, Indonesia. Today, I will present my research with my thesis supervisor with the title of Study of the Heat Loss Effect in Geothermal Steam Production Well. This is the outline of this presentation. First, we will start with introduction that consists of background and purposes of this research. Next is methodology that consists of flow process of this research. Next is case study that consists of well data that is used in this research. Next is result and discussion from this research. And the last one is conclusion and recommendation from this research. First, we will start with introduction. As we know, geothermal production well is a main component of the geothermal production facility and also a geothermal fluid flow media that connects the surface and the reservoir. A geothermal well is similar to oil and gas well that consists of casing and cement. During the geothermal production, it will be changed in the characteristic of geothermal well, such as casing and cement temperature will increase. That is due to heat loss of the geothermal fluid. During the geothermal production, the heat transfer will occur in the well by conduction and convection heat transfer. The convection heat transfer is the heat transfer that occurs between the geothermal fluid and the inside of production casing, and the conduction heat transfer is the heat transfer that occurs between the casing and formation. There are several factors that influence the heat transfer in the well, such as well, cement, and formation specification. The fluid characteristic is also influence the heat transfer in the geothermal well. The heat transfer will cause the temperature change in fluid, casing, and cement. This is several purposes from this research. First, this research is development of heat transfer model in the steam production well. Second, this research is to predict the steam heat loss and its effect on every 100 meter well increment when the steam is produced, and to predict the temperature distribution of casing and cement and their effect on every well segment. Next is methodology. This is the flow diagram of this research. This research is start with literature study that supports this research. From the literature study, we will get the well data that we need for this research. Next is well data interpretation of one geothermal well. Next is development of heat transfer model and calculation using well sim. For heat transfer model development, first we input the parameters of casing configuration, well geometry, and formation temperature. Next is pressure drop calculation using homogeneous flow model. Next is heat transfer model development by input the heat transfer equation. Next is heat loss calculation, and we will get the fluid pressure and temperature from heat transfer model calculation. And then for well sim calculation, we start with input parameters. That parameter is similar to the parameters that we use for heat transfer model calculation. Next is calculation with well sim simulation with bottom-up calculation, and we will get the fluid pressure and temperature from well sim simulation. Next is comparison of model result and well sim result. If the model is not matched with well sim result, we must check the heat transfer model development, such as we must check the equation of heat transfer or the input parameter to heat transfer model. And if the model is matched with well sim, we can continue the next calculation, such as heat loss calculation every 100 meter of well increment, and casing and cement temperature calculation and distribution. There are several limitations from this research. This model is using the Fourier's law and Newton's cooling law. That the Fourier's law is used to conduction heat transfer calculation, and Newton's cooling law is used to convection heat transfer calculation in cylindrical media, and is also using the Remy heat transfer that was developed by Horner and Shinohara to calculate the steam heat loss. And then this research is also the pressure is calculated using the homogeneous flow model in this research, and this model is developed in the steam production well during the production activity. And then there are several assumptions that is used in this research. First, the well static temperature is assumed as the initial temperature of casing, cement, and formation. Second, the formation temperature is assumed to be unchanged because the condition of heat transfer is there are a different temperature. In this research, the different temperature is between the geothermal fluid and formation. And the last one is the heat transfer that is occurred in liner is neglected because in the liner there are several production zone, and we need the reservoir simulation to calculate the heat transfer in the liner. Next is case study that consists of well data that is used in this research, and well A01 is used in this research. We have composite log of well A01. From the composite log, the continuous period is at depth of 707 meters and is assumed as top of reservoir. And from formation lithology, there are two indications of formation lithology. First is andesite is at depth of 0 until 300 meters and 459 until 1,600 meters, 600 meter, and the second one is glaciative from depth of 300 until 459 meters. And we have the pressure and temperature static of well A01, and this is the graphic of PT static of well A01. From the graph of PT static, the temperature static is higher than the boiling point per depth or BPD, and is assumed that the reservoir fluid of well A01 is superheated steam with the reservoir temperature of 224 degrees Celsius. Next is result and discussion of this research. This is the result of model and well sim comparison. The comparison is conducted to validate the model result with the well sim result before being used for next calculation. And from the graph of pressure and temperature of model and well sim, the steam pressure and temperature of model is matched with the steam pressure and temperature of well sim. It is shown that the trend of pressure and temperature of model is the same trend of the pressure and temperature of well sim. And from this result, we can conclude that this model can be used for next calculation. And then this is the result of steam heat loss calculation. From the graph of heat loss of at every increment, the steam heat loss is less than 2 watt per meter at every increment, and the steam heat loss is increased along with the increase of well increment. And then the formation temperature drop is also calculated in this research. The formation temperature is increased along with the increase of well increment. And then from the graph, the steam heat loss and the formation temperature drop is increased along with the increase of well increment. And we can conclude that the formation temperature drop could affect the steam heat loss. And we can get the correlation that the heat loss of steam could be higher along with the increasing of formation temperature drop. And then this is the result of temperature distribution of casing and cement. And this is the result of final temperature of casing and cement at every well segment. With the segment 1 is at depth of 0 until 30.5 meters, and segment 2 is at depth of 30.5 until 459 meters, and segment 3 is at depth of 459 until 784 meters. And from this result, the casing and cement temperature is increased during the production operation, with the initial temperature is similar to the formation temperature, and there are different temperatures of every casing and cement. From the result, the heat of steam is estimated not completely transfer into the formation because the heat loss is very low, or less than 2 watt per meter, and the heat of steam is estimated only transfers to the surface casing. It is shown that the temperature difference of surface casing and surface cement is large, and the temperature of surface cement, conductor casing, and conductor cement are close to the formation temperature. And this is the visual of temperature distribution of casing and cement every segment. And from the result, the material thermal conductivity and the thickness layer of well segment could affect the steam heat transfer. It is shown that the temperature increasing of casing is higher than the temperature increasing of cement. And because the thermal conductivity of casing is higher than the thermal conductivity of cement. And then cement can reduce the heat of steam. And the segment 1 layer is thicker than the segment 2 and segment 3 layers. It is shown that the segment 1 have 3 layers of casing and 3 layers of cement. And the heat of steam in segment 1 is estimated only transfer into the casing surface. It is shown that the cement, the surface cement, casing conductor, and cement conductor temperature are close to the formation temperature. And we can conclude that the casing and cement could have a lower increasing temperature along with the lower of material thermal conductivity and the thicker of the well segment layers. In this research, we use 75 watt per meter Kelvin for casing thermal conductivity and 0.5 watt per meter Kelvin for cement thermal conductivity. And next is conclusion and recommendation from this research. There are several conclusions from this research. It can be concluded that the heat transfer model result match with the Wilson result. Then this model could be used to calculate the heat loss of steam and the temperature of steam, casing, and cement. The heat loss was very low during the steam production. Then the heat of steam won't completely transfer into the formation. The heat loss of steam could be higher along with the increasing of formation temperature drop. And the material thermal conductivity and the thickness layer of the well segment could affect the steam heat transfer in the production well. And then there are several recommendations from this research for further research and the usage of this model calculation. This research needs to be validated with laboratory scale experiments or the field measurement. This heat transfer model can be developed with other pressure drop correlations such as Briggs and Brill correlation, Higginbotham correlation, or safety correlation, and so on. And also can be developed for water-dominated production well and two-phase fluid production well. And for the usage of this model calculation is recommended to be conducted before the drilling activity in the casing and cement design to reduce the risk of drilling activity such as the thermal shocking at shallow depth of geothermal well. And then there are several references that support this research. That is all. Thank you.
Okay, thank you for this opportunity. Assalamualaikum warahmatullahi wabarakatuh. My name is Gali Kusumo from Geothermal Engineering, Bandung Institute of Technology. At this time, I would like to introduce the applications of artificial intelligence for prediction of geothermal reservoir productions. The outline of my presentations, the first is about the backgrounds, methodology, result and discussions, and the last is about conclusions. For the backgrounds, as we know that a reservoir is the main asset of geothermal exploitations, means that the problem in reservoir will affect to the continuity of the business of geothermal exploitations. And as we know that a reservoir has heterogeneous properties, it means that it consists of the uncertainty. And then currently, the reservoir production modeling use certain assumptions parameters. So it needs collaborations with the geoscience study engineering to build the reservoir production modeling. And then we know the challenge that there is a lot of data recorded on the geothermal operations that had not been properly utilized. And then the development of artificial intelligence offered the opportunity to be applied to the geothermal. And the last, about the development of computer technology. And then we have an idea that they use the artificial intelligence as the alternative method in the reservoir evaluations. Currently, the use of artificial intelligence is widely used in our lives. In the energy sectors, for example, for the oil and gas, as we know that now it has been commercialized. For example, the Baker Hughes that announcing the Baker Hughes C3.ai and then Schlumberger collaboration with the Dataiku partnerships, and they will enable the enterprise scales of artificial intelligence in the exploration and productions. So the Halliburton. This idea and the methods we will implement into the Patua geothermal fields. That's the complex fields that consist of 10 geothermal well and 1 injection wells. The total production is November in 2019. Oh, sorry, 2018 is about 360 tons per hour or 100 kilogram per seconds. This is a steam-dominated geothermal field. The brief methodology of the study is consists of, in general, consists of 3 parts. The first is about data preparations, that consists of data processing and determine input and output. Data processing consists of the data cleansing, data normalizations, correlation analysis, and the lag plot analysis to show the continuity of data. And then we build the artificial intelligence architecture by using the Python with the PyCharm as IDE, integrated development environment, and then supported by the project interpreters such as NumPy, Matplotlib, Neuralab, Pandas, Seaborn, Scikit-learn, and CP. And then after we build the architecture of artificial intelligence, we do the train and we validate the models. And then we validate the model by using the calculation of mean absolute percentage error. After that, we have the reservoir production model to prediction model. This is the architecture of artificial intelligence. We use the artificial neural network for this model that consists of input layer, hidden layer, and output layer. For each layer, it consists of the neuron that connected by the dendrite pathway, cause it called a weight factor. And based on the study of the data processing that we said before, that we set the input parameters as the wellhead pressures, wellhead temperature, trim valve open, megawatt, and reservoir pressures. And we have to predict the flow of geothermal wells. It's called flow rates for the predictions. To know what is the best training algorithm that can implement to solve the problem that we have faced in the study, we have 2 alternative training algorithms. The first is about Newton conjugate gradient algorithm and the Broden-Fletcher's Kohlfarbs-Sano algorithm. And then to know what is the training method that the best solutions for the problem in our study, we use 3 kinds of method. The first, it's about the show in the figure A. It consists of only the percentage of use of data for training and the percentage data for the validations. We use the method 1 that's shown in figure A, and then method 2 shown in the figure B. And the last, the method 3 is the we developed another method. It's called figure B with the random data. This is the illustration of simple implementation in a single well. We have production data, in this case mass flow, that we have to predict. In 700 days we have the actual data, and then we delete about 40% of the last 700 data, and then we use the remaining data to train the artificial intelligence. And then we simulate after we train, and then we simulate. So we have data predictions, and then the comparison between actual and predictions, we calculate the error. The error in this study, we use the mean percentage absolute error. So the two ways of this, what we do in this simple implementation. The first, the AI model that has been trained is used for prediction simulation, and the second, we calculate of the error of actual value and prediction value by using the mean absolute percentage error. And then, as we introduced previously, that we have two kind of algorithm, Newton conjugate and also Boulden-Fletcher. We show that the Boulden-Fletcher-Coaxial is the best algorithm that provides optimum in results. We saw in this graphic that this is better than the Newton conjugate. And then next, about the variations of training method. We have three kinds of training methods. The results show that the random training provides the minimum results, with the number of average error is about 1.6% in average. It's a mean absolute percentage error. And then the conclusions of our study. The first, the artificial intelligence model for precision geothermal reservoir production with the steam flow as input parameters has been successfully developed by looking the mean absolute percentage error that we said before. And then the second, the BFGS algorithm, Boulden-Fletcher-Coaxial, is an effective algorithm that in implementations of the prediction of model in the study. And then the third, the random methods of training and validation produce the minimum error with the minimum data usage. And then the fourth, the minimum average error values in the study is about 1.6 by using the BFGS algorithm and the random training methods. That's all. Thank you, and wassalamualaikum warahmatullahi wabarakatuh.
PT Coaxial Daya Bersama adalah perusahaan ketenaga listrikan di Indonesia yang beroperasi di seluruh wilayah Indonesia dari Sabang sampai Merauke. Coaxial didirikan pada tahun 1998 sebagai anak perusahaan PT Indonesia Power dan bagian dari PT PLN Persero. Coaxial memiliki 4 bidang usaha, yaitu suplai energi, jasa operasi dan pemeliharaan pembangkit listrik, jasa gas dan diesel engine, dan jasa maintenance, repair, overhaul, MRO. Dalam kurun waktu lebih dari 2 dekade, kami telah mengembangkan bisnis kami secara signifikan dan membangun dasar yang kokoh bagi portofolio perusahaan di level nasional maupun internasional. Coaxial menawarkan satu solusi layanan terintegrasi di bidang ketenaga listrikan melalui Coaxial Integrated Solution. Dengan menggabungkan kompetensi, teknologi dan pengalaman, kami yakin dapat membantu para pelanggan mencapai efisiensi dan keandalan pengoperasian pembangkit listrik di Indonesia dan seluruh belahan dunia. Coaxial, trusted partner for power generation.